Welcome to the demonstration of our robotics peg-in-hole simulation. We start in the development environment, launching the Flask-based application and initializing the PyBullet physics engine. As the server starts, we transition to our custom web dashboard. By clicking the Creator link at the top, we briefly open my LinkedIn profile. Feel free to connect with me here. The dashboard provides a comprehensive view of robotics cell. On the right, we monitor live telemetry, including joint positions and end-effector pose. Now, we navigate to the double robot workbench. This interface provides a dual overview, allowing us to manage and monitor two separate robotic cells simultaneously. We configure Robot 1 for the left cell and Robot 2 for the right cell, both targeting a normal surface. By starting both, we initialize the dual simulation. Let's execute the primary task. Starting on a normal, flat surface, the robot perfectly executes the pick approach and aligns the cylindrical peg. Increasing the complexity, we switch to a 15-degree inclined surface. Watch the telemetry as the robot adjusts its wrist force and joint positions to compensate for the angle. Now testing the steep 45-degree incline. The vision system maintains high confidence, and the Conjugate grasp ensures a precise geometric fit, keeping the grip highly stable despite the challenging angle. Task complete. The system automatically generates a detailed simulation report. You can download in any format. Following the insertion, the system enters the extract state to safely remove the peg. It then executes the return to pick command, smoothly resetting the robotic arm back to its starting coordinate slot. We then return to the dashboard to initiate a new task on a 30-degree incline. Here, we open the Aria AI Assistant. We can ask the AI to explain the workbench functionalities or query it on how to improve grasp quality. It acts as an integrated copilot throughout the simulation. Next, we test complex geometries on the sculpture surface. The robot is tasked with inserting a triangular peg into a domed target. The slip detection system shows 0 mm of drift, ensuring absolute precision. With the dome insertion complete, we generate another comprehensive word report, downloading the specific telemetry and event logs for this highly complex run. Finally, we transition to the Color Sort Workbench. Mixed shapes are fed onto the conveyor. Watch as the robot accurately identifies the orange cylinder and seamlessly routes it to its target zone. Next, it successfully processes the blue triangle. While we conclude the visual demonstration with these two examples to keep the overview concise, please note that the system processes remaining queued items, such as the green square, utilizing this exact same automated precision. From the left navigation panel, we transition to the Congruent workbench. An initial operator guide outlines the core parameters. This briefing provides essential details on surface setup, tracking the insertion trace, and monitoring geometric alignment. Closing the guide, we enter the isolated dashboard to evaluate the precise geometric fit across different surface types.